everybody knows what he's talking about.
Yeah, thank you for the invitation to this workshop. So I'll just continue where Michael stopped. So I would just want to point out, first of all, that he left this question open. So whether a standard, the standard definition of hitting set for VP bar, the verification problem of that, right? So you guess a set and you want to certify or you want to verify whether it hits VP bar, and that verification you want to do in p-space. So the best that is known currently, or before our work, the best that was known was verification can be done in exponential space. So one corollary of our work would be that this can now be done in p-space. Okay, so without the robust thing. So just hitting set for VP bar, certification we'll see is now possible in p-space. But since this is a GCT crowd, I should rephrase some of the main results as so in geometric terms upfront, without going into my polynomial notation. So, so you can keep this setting in mind. There is the space f to the n. F is a field, and we'll want it to be algebraically closed because we want to use algebraic geometry. But we won't need any assumptions on the characteristic. So characteristic can be p equal to 2 or it can be 0, whatever. So suppose you are given a map from this space to itself.
So can you use some other thing? Can I use a definition?
Yeah, let's try. So suppose you are given a polynomial map from the space f to the n to itself, right? So this is given via n polynomials. So these are n variate n polynomials. So on any point alpha bar, what it is doing is it is computing the coordinates f1 at alpha bar, f2 at alpha bar, dot dot fn at alpha bar. So you get another point in the same space. So keep this. So think of this as the input. You are given FIs.
It's not working.
Yeah, so there is.
It's the angle of the.
It's the angle, yeah,
it's
right.
pointing up or down.
Right. So you are given this. You are given this polynomial map. The definition is given to you in the input, and that you can see as defining this this action. And we want to study the properties of image of this map. Okay, so we will be interested in two problems. First, I'll call algebraic dependence problem. So this is, so you look at the image of f, look at its Zariski closure, which thankfully I won't need to define here. Like everybody knows what this is. So what is the dimension of this? Is it less than n? So this is. So the first point is that although you already know what is the definition of closure, it may not be immediately clear that here the closure is actually a variety. Okay, in general, for an arbitrary set, when you close it, you may not get a variety because it may decompose into varieties. So it may be decomposable, it may not be irreducible. But here, since you are looking at the image of a polynomial map, you can actually prove as a homework exercise that the closure is a variety. Okay, so is the dimension of this variety n or smaller than n? So you want to distinguish between the two? Yes?
That's the same as whether there's a polynomial, a non-zero polynomial that vanishes on it?
Exactly. Whether there is an annihilator. So this is the question of algebraic dependence, whether these polynomials are dependent or not. So when the dimension is less than n, they are dependent, otherwise they are independent. Okay, so you want to distinguish between these two things. But here is the geometric meaning of that. Second question I'll call zero enclosure, which, as the name already suggests, you want to check whether 0 is contained here. Okay, so the point 0, whether it is contained in this variety. So this is the question which, I mean, it's a very, it may not be clear at this point, but it's a very, very expressive problem, and it can actually capture any problem of interest in approximative complexity. In particular, you have seen null cone problem in this workshop. You saw this question of verification of a hitting set for VP bar. All these questions very easily in a standard way will reduce to this. Okay, so this is the problem of ZC for us, and what we actually do is we give a p-space algorithm for this. Okay, and this will be, the method will be completely characteristic independent.
And does the second question solve the first one?
Oh no, yeah, so okay, what do we show for these two questions? No, so the first question is much easier.
I see.
So what we'll show is that this is an AM intersection co-AM. So these are our main results. So the question of algebraic dependence will show that it is an AM intersection co-AM. So in particular, it could not be NP hard. In fact, if you are working over complex, there is a randomized polynomial time algorithm. So over complex and sufficiently large characteristic, this is actually practically a solved problem. But for low characteristic, it is still open. And we showed that, I mean, it wasn't even known whether it is in the polynomial hierarchy. This work shows that it's in AM intersection co-AM. For this, we show p-space. The previous best was X space, especially for finite fields or finite characteristic. There was nothing better than X space known. Right, so in the future we would like to show this to be in BPP. So a practical algorithm for this, and we would so as Ketan has challenged us, this needs to be put in PH, the challenge is interesting because he says that if we put it in PH, then we'll get an alternative for GCT.
No, I didn't say. There is a serious possibility of it.
Right, so with that qualifier, it becomes an interesting question.
Nitin, just to make sure the first result is not under GRH, and when the strengthening that we are asking for under the second, for the second is under GRH.
No, there is no GRH.
Okay.
Forget about GRH. So everything here is unconditional and mathematical proofs.
And second one implies?
Right, so these problems, these other problems like verification of hitting set for VP bar or the question of null cone problem, these are all very special cases of ZC. In fact, as Avi pointed out, null cone problem is expected to be in NP intersection co-NP. This problem is not. This problem actually has again as a homework exercise, you can show that this is NP hard. So this problem, the best you can hope is AM. You cannot get below NP. Okay, so I'll give a more, maybe a more explicit definition of this. This is the algebraic geometric definition for ZC, but there is a more palatable definition. So we'll see that in the slides. We'll see, in fact, two more ways to define this problem. Something happened.
Just hit.
Okay. Right. So the first, the AD result is that AD is not hard, and the second GCT Chasm is filled by showing that ZC is in P space, but it's a much more general result than just filling the Chasm. I mean, Chasm dates preceding this workshop. So in this workshop, it has been redefined now. So now the Chasm is bring it down to anything below P space. Okay. Okay, so now let us go through these things a bit more carefully. So when do I have to stop?
Your last
5:15.
continue.
5:15, okay. So the question of algebraic dependence testing is you are given polynomials f1 to fm. They are n variate over some field, and we'll call them algebraically dependent if there is a non-zero annihilator, right? Which means that you substitute f1 to fm in A and you get 0. So, and it will not be very important, but you can assume the input polynomials to be given by algebraic circuits. So in particular, they may have exponential degrees. So once you have this notion of dependence, so this is naturally generalizing the notion of linear dependence, right? So we are actually trying to generalize linear algebra to non-linear settings, and you get a notion of rank out of this. So that is in the literature it is called transcendence degree, because it is something to do with field extensions, transcendental field extensions. So we'll continue with this. You could also call this algebraic rank. So for polynomials f1 to fm, the algebraic rank or transcendence degree is the maximum number of algebraically independent polynomials in the set. So simple example is if you look at x1 plus x2 and sum of squares, depending on what characteristic you are in, it is either these two are independent, so the transcendence degree is 2. So this happens in all the cases except when the characteristic is 2, because when characteristic is 2, you can see that the second one is square of the first. So in that case, the transcendence degree is 1, otherwise it is always 2. You can also, it is easy to show that this notion is actually independent of algebraic field extensions. So you can go to algebraic closure of the base field and still the transcendence degree would not change. Okay, it is invariant up to algebraic extensions. So we can assume that f is f bar for this talk. And problem of ADF is defined as given these polynomials in some form, test the algebraic dependence over this field. Okay, so you just have to answer yes or no. And the quantitative version will be compute the transcendence degree. So it is not really clear whether this problem is computable, just by the definition, because you don't really know how big the annihilator is, right? So this problem could have been uncomputable as well. But it is not, it is actually computable, and so then the questions which are open are more to do with the computational complexity of this problem.
The annihilator itself is polynomial?
Yeah.
Oh, no, so the annihilator usually is very difficult.
But it's a polynomial.
It's a polynomial.
Polynomial.
Oh, okay, not polynomial size.
No.
That's right.
It's a polynomial.
Yeah, okay, yeah, so it is a polynomial, yes. But will that change anything? I mean, you could have,
No, it's just
Question. Yeah.
right, okay. I mean, even if you think of it as power series, I think it will have the same effect.
But the usual definition is that it's a polynomial. That's the,
Right,
that's the
yeah.
definition.
Okay. And so yeah, so you can ask, is the annihilator special? So in the next slide we'll see that actually there is a classical degree bound for the annihilator, but we cannot say anything more than that. So usually annihilator is hard, and there is a result by Neeraj that it's even very simple questions about the annihilators, if you ask, they are like Sharpie hard questions. So what are the applications, or where does this concept appear? So this is fundamental in commutative algebra and also in algebraic geometry, because, well, as I have already defined AD in that form, it's a question about dimension of that variety. And in computer science, it was used to design these algebraic pseudo-random objects called extractors. And so in fact, that picture of polynomial map is basically inspired from this. And then it was used to prove lower bounds for circuits and also to design hitting sets in several works. Specifically, the concept of annihilators has been used recently. It was already there in Heinz and Schnorr, and then recently it has been used to prove bootstrapping of variables results for hitting sets. And so this work gives another application of annihilators, which will be to solve the question of ZC. So there actually we'll work with annihilators and try to find properties of it, which will be equivalent to ZC. So we'll see that actually the question of ZC is related to polynomial system solving, and it is also related to questions in GCT. Any questions at this point? Okay, so I'll quickly go through the previous results of this question of algebraic dependence. So it's a classical result, and it's a tight result that minimal annihilator has degree at most product of the degrees of the polynomial.
What do you mean by minimal annihilator?
Oh, so annihilators may be infinitely many. So
The smallest degree.
Huh?
Of the smallest degree.
of the smallest degree.
Minimal is one of the smallest degree.
One of them.
Yeah, so depending on how small the dimension of this variety is, I mean, if it is n minus 1, then there is minimal is unique because the annihilating ideal is principal. But as soon as you go to n minus 2 dimension, it becomes crazy.
If at all there is an annihilator, there is one of this much degree. Right, that's what it is.
Yeah.
So there is yeah. So you can read this as saying there is at least one annihilator.
I mean, if there is.
No, for in the first case, so when the dimension is less than n, there is at least one annihilator with degree product of degrees of the input, and it's tight. And so what? So that bound is simply it's an exponential bound. It's simply exponential, and or it is singly exponential. And since the number of polynomials is only m, the number of coefficients or the number of monomials in this annihilator, they are only exponentially many. Okay, they are single exponentially many. So using this, actually you can set up a linear system to basically you are trying to find the coefficients, the unknown coefficients of the annihilators. And this linear system is exponentially large. You can solve it in p-space. Okay, so you have shown that algebraic dependence problem, irrespective of the field, it is in p-space. So this is the computational, the complexity upper bound. And so there were some improvements on this known. Yes.
Depends on the numbers that are written there, right? So p-space in some. If pi is written there, you can't even compute it.
So if you think of arithmetics or algebraic circuit representation, then think of the bit size. For the circuit, also take into account the bit size.
If you have a matrix and pi is written there.
No, pi is not written there. The bit size, not just the size of the circuit, but also what are the constants. If you want to do explicit computation, then you have to look at bit size. So below p-space, there was a result. It is not very important what this is, but it is just something below p-space, not yet in polynomial hierarchy. Okay, so it's something between p-space and pH. So the thing is that this result does not need any restriction on the field. Okay, this is true in general. When you look at special fields, so when the characteristic is 0 or it is sufficiently large. So large actually just means larger than this Perron bound. So as long as the characteristic is 0 or bigger than Perron bound, then there is a very nice classical criterion which is called Jacobi's criterion. So you look at this Jacobian matrix, which is just the first order partial derivatives of your polynomials. So it's an n cross m matrix. And so this is a symbolic matrix. The entries are polynomials. So over the function field, whatever is the rank, that is equal to the transcendent degree. Okay, so the question reduces to just checking a determinant of a symbolic matrix, which you can solve in randomized polynomial time by fixing the variables. So where does it fail when the characteristic is not 0? So the failure, so actually it can be shown is that the proof works as long as this field extension is separable. Now if you don't know what is that, just ignore this statement. But if you know what is separability, then this criterion is actually just dependent on separability of this field extension. So when the characteristic is 0 or it is large, this extension is always separable without any assumptions. When the characteristic is too small, then there are bad cases when this could be inseparable. And then the criterion fails. Once it fails, it is very hard to find a different criteria. I mean, it's always, so it is still an open question, how to characterize algebraic dependence or independence. So separability just means that these variables xi's, they have distinct conjugates. Okay, so when you look at this xi over this field, the conjugates in the min poly, they are distinct. So as long as that happens, the criterion works. And there is a result that extends this criterion to limited inseparability. Okay, it's not a general result, but when there is inseparability, but it's only constantly large, in that case also there is a smooth extension of the Jacobian criterion.
These criteria are like polynomial time decidable.
Right, so when I say constant inseparable degree, then it is.
Yes.
Then it is polynomial time. It basically reduces to linear algebra in some space. You have to make sure that space is not large, not too large. Any other questions?
When the minimal annihilator has a degree that's equal to the product of
Yes.
figures, does that tell you something about, like, is that a property that's meaningful in some sense? Does it have any connections?
It is not clear. I think for generic instances that will be the case. Okay, so let me now move to the first result, which is that this question of AD is in AM. Okay, so for that I will rephrase, which I've kind of already done. I will rephrase this question of AD to polynomial map and its entropy. So consider the map bold F from the space F to the n to F to the m, where n is the number of, so n was the number of variables and m is the number of polynomials given to you. So from now on I will assume that n and m are equal and that the field is actually algebraically, well, field is big enough. So these slides will be interesting only in the case of finite field, because already for complex or characteristic 0, the problem is simple. The problem of AD is in BPP. So think of F as a finite field, just big enough.
So
Yes.
what you said before is you can always go to an algebraic extension.
Right.
So you can just make the field big enough if you want.
Correct, yes. But I don't want to make it infinite, because in the protocol, in the AM protocol, I need a finite field.
Okay.
Yeah, that's all. So I want to still keep it finite but big enough. So these assumptions, yeah, I don't want to go into it. It's again an exercise to show that if you solve this case, you solve all the other cases. So we just take n to the m. So what can we say about the geometry or the entropy of the map? So the questions you can ask are of the following type. What is the dimension of the image? And what is the dimension of the pre-image? So basically fix a point here and look at the pre-image. What can you say about the pre-image of a generic point here in the image? Right? You can ask these questions. You can also ask the question about Zariski closure of the image, which will be the second question. And I'll just remark that these questions seem unrelated to the ideal F1 to Fm. Right? So the thing given to you in the input is this set of polynomials, but if you look at the ideal and if you look at the zeros, the variety, that doesn't seem to have any relationship with these questions. Okay, because you are not looking at the zero set of F, you are actually looking at the image of F closure. So this is a completely different object. So our solution, the ideas here will also be very different. We'll not be looking at, it's a different variety. It's not the variety ZF. So the entropy behavior here should follow the following intuition that when these polynomials are independent, then you would expect the image to be large. Okay, so the proof is by example. We take F1 to Fm as x1 dot dot xn, and in that case the image is the whole space. So you generalize this and imagine that, okay, in general also when the polynomials are independent, then this space the image will essentially be very close to the whole space. Okay, and when the polynomials are dependent, then the image will shrink. Okay, so this is the basic intuition, and we basically formalize this to get these two protocols. Okay, so we show that AD has a protocol, and we show that complement of AD also has a protocol.
So is it like analog of a shrunk space?
Not sure. I think it's even simpler.
By the way, in general case, the symbolic rank of Jacobian, is it like lower bound on your algebraic rank?
What do you mean lower bound?
So again, you compute the symbolic Jacobian and compute
Right.
it rank.
Right. So over.
Is that bound for the thing which you're looking for?
So for the field of complex or characteristic 0, it is equal to
Yeah,
transcendence.
but in general, is that the bound?
In general,
Yes.
It's a lower.
Yes.
It's lower bound.
sure. Yeah. So whatever is the rank, yeah, that is less than equal to transcendence degree. But it could also be 0, because if you just simply look at x to the p, then the Jacobian is actually 0. So okay. Yeah, so the notation that will be of help here is this pre-image notation. So you take a point B, which is in the image, and look at the pre-image. So this F inverse B is a set. So I call that pre-image, and image is clear. It is just small f of this f to the n. Right? That's the image. So the two sets are image of f, and you. So let me call this A. So you basically go to the image of A and then look at F inverse. So this will be the pre-image. So these are the two sets, and basically we'll show that in one case the image is big, in other case pre-image is big, and then the AIM protocol will just distinguish that.
So here, large is only kind of relative because these polynomials have exponential degree.
Yeah, sure, yes.
So large really means just like one and exponentially small.
Yeah. So the thing is, in these AM protocols, you only need a doubling. So as long as the numbers are m or whatever, y and 2y,
Yeah.
you have a protocol. But y itself can be exponential.
So my intuition is that like large means something like 1 in the degree, where the degree can be exponential in the circuit size, and small would be something like 1 in the field size.
No, but it says it doesn't matter. It doesn't matter. You just need to
Yeah,
separate
but
the
the
size.
field size, when you say it's large enough,
No, the field size being large enough.
means it needs to be like more than an exponential.
Yeah. So field size, think of the field size as bigger than product of degrees,
Okay.
something like that, or product of degree whole square.
Yeah.
Yes.
It's just an approximate lower bound protocol. So it
Yeah,
doesn't
but I'm
matter.
saying, but-
Whatever small, how they relate to the
Right,
big
right.
Yeah,
universe.
but to make this, the small has to be bigger, has to be smaller than the large.
Yes, yes. Good.
No, so his question was about the field actually. How
Yeah.
big should the field be? Yeah. So field also will just be product of degree whole square, something like that. Yeah. Right. So say the finite field is Galois field of size q. Q is a prime power. So for something in the image, F inverse B, the size of that set we'll denote by big N B.
So what was the entropy? There was some entropy in the title.
Right. So this entropy is, I have rephrased this question of transcendence degree to entropy of this map. So for the polynomial map, it is interpretation with entropy, and or you can also in this term it is algebraic geometric. So whatever. And the first definition was completely explicit, that what is the max number of algebraically independent polynomials. So there are kind of three interpretations. So actually I don't want to get into the proofs of this. I'll just very quickly go through this slide. So where I want to study the pre-image. So what is the difference? So suppose the polynomials are algebraically independent, right? So in this case, so when the polynomials are algebraically independent, the intuition is that image will be large, and a parallel intuition is that pre-image will be small. Okay, so this is what the lemma is saying, that for algebraically independent polynomials, if you look at the pre-image of f of a, so f of a is b here, and look at the pre-image of that, then that is small, where small is with respect to this d, product of degree. It is smaller than this for almost all the points in the domain. Okay, but so how is this proved? Well, this is proved by looking at the relationships between xi and on these polynomials. So since these polynomials are all independent, they can actually generate any variable xi. And when you look at the relationship, that has degree at most d. And using that, you can get this result. Using the fact that a degree d polynomial has a low density of roots in the big space. But I won't go get
using the bound that you have on the degree of the minimal annihilator.
Yes, exactly. Yes, but I don't want to go into this. And it also actually will imply that the image has geometric dimension n, and the pre-image has dimension 0. Okay, so the dimension of generic pre-image plus the dimension of image is equal to n. But it's extreme, it's 0 and n. You want to think of this geometrically. The other case is when the polynomials are dependent. So in this case, you would expect the pre-image to be large, and this is what we are saying, that for almost all the a's, for a high density of a's, the pre-image is big. So you fix here k to be d or 2d. So then here you have the pre-image bigger than 2d, and there you had pre-image smaller than d. So you have a gap. Okay, so this gap gives you an AM protocol. Yes.
I just wonder how this, you're basically approximate the entropy of the output in this.
Yes.
There's this paper a few years ago of Vir and Salil Vadan on approximating the entropy of polynomial maps for finite fields. How is this? Some of their protocols are actually in BPP, some are in statistical zero knowledge, which is both below this. So how does it, is it related, these results there?
So some of the lemmas here may give an efficient, using sampling you can implement them. But
this subsumes it, or it's more general in terms of the fields you can use? Because some of the results are more efficient.
So to answer that, I have to read that paper. I don't know.
So you don't know?
No, see, that paper actually, you define the rank to be the rank of the Jacobian, and then
yeah.
No.
So then it completely fails then, because
that is not. Here you are doing algebraic independence testing, but there you say that suppose you have a polynomial map such that the Jacobian has large rank.
I thought they were just given the family of polynomials, and you just ask what's the entropy of the output of the image. That's the question. Just approximate the entropy of the output. But anyway, we don't have that.
Right. Yeah, so it's a good point that these methods do not depend on the characteristic and also do not assume anything about the Jacobian. So even if the Jacobian did not exist, we did not know about it, still all these things hold. So this is actually the point of the first result, because otherwise you have a practical algorithm when the criterion works. Right, so then just using a standard method on this set, you have verified AD in AM. And symmetrically now, or analogously, we look at the image now. So in the independent case, you expect the image to be large, which means that for a good fraction of the B's, there should be some pre-image, right? So this is just a rephrasing of that. This again is a play with the annihilators. And in the dependent case, the image should be small. So for most of the B's, there should be no pre-image. And Now you should look at image of f. So if you use so the AM protocol will be biased towards the case when the polynomials are independent. So AD bar gets certified in AM. So AD is in co-AM. Okay, so we have shown that, this is a very high level sketch of AD is in AM intersection co-AM. Any questions? Okay, so then let me proceed to the, and in particular it rules out that AD is NP hard, because if AD is NP hard, then pH will be sigma 2. So we don't expect that. Unfortunately, this method does not give any algorithm at all. So algorithmically, all these arguments are useless. It's only a complexity evidence that the problem is not NP hard, but it does not really give us any algorithm or any heuristic to actually solve or to test algebraic dependence in any special case. Okay, so now I want to move to the second problem. So I'll present it in 3 ways. So the first is this, where you are given polynomials, you look at the image of f and then close it. Okay, and the question is whether it contains 0. So what is the meaning of closure? Well, Zariski closure is basically you, so in general, if your set is image of f, so for a set S in the space, S bar is basically defined as, look at all the polynomials that vanish on S. Okay, so the set of those polynomials will form an ideal, and look at the 0 set of that. Okay, so it is possible that S bar does not increase, it is equal to S, but usually it will increase. If you start with an arbitrary set which is not a 0 set, then it will increase, and you can also see this as a limiting process. So the limit points have been included, but this is of course very algebraic. I mean, even to see that this notion coincides with the Michael's notion over complex or over reals is a non-trivial exercise. Okay, but this is a completely algebraic way to define Zariski closure without invoking analysis or without taking limits. So we'll continue with this. This I think just needs that f is algebraically closed for proving interesting theorems. So this is also the smallest affine variety. So it becomes a variety because our set is very special. It is image of f. So in this case, it is actually a variety. In general, S bar may not be a variety. It may decompose. For example, if you take S to be 2 points and you try to close it, so then obviously it will be decomposable, right? But that will not happen in this case because here you are looking at image of a polynomial map. So it's a interesting enough case that the closure is a variety, and it's the smallest affine variety that contains it. Yeah, so this you can skip, this you already know. So an illuminating example is if you look at these two polynomials, x1 and x1, x2 minus 1. So in the image of this polynomial map, you don't find 0, right? Because, well, 0 would mean that x1 is equal to 0, but then if x1 is 0, then this evaluates to minus 1. So there is no chance of 0 being in the image. But so what happens when you take the closure? So when you take the closure, you will be surprised to know that you get to the whole space. Okay, so in this case, actually the closure is f square. So every point is actually a limit point.
So if the points are algebraically independent, then the Zariski closure is everything.
Exactly. Yes. That's the result. This is exactly what happens here. So these two are independent. So this actually you can deduce from the definition. So if the polynomials are independent, then the annihilating ideal is 0, and the 0 set of 0 is everything. Right, so in this sense, you already get, in this example, you already get the insight that we are strictly generalizing polynomial system solving. Right? So you are given polynomials. If you wanted to find roots, that was the question of whether 0 is in the image. If you look at now a closure of the image, that's a different question. It is not the question of polynomial system solving, but we'll see that we'll see later that it's actually a natural extension of polynomial system solving. So how do you solve this? So ZC, I mean, you can try to find this I explicitly. So you are given polynomials, you try finding, computing the annihilating ideal by finding its generators. And everything can be bad here. The generators may be exponentially many. The degree and the complexity of the annihilators could also be exponentially large. And things could even be doubly exponential actually, because you are using elimination theory here or Grosvenor basis. So you actually can solve this in X space, which is doubly exponential time, and the annihilating ideal may be terribly complicated, which it is actually in most of the cases. Yes, there was a question.
The degree bound that you gave earlier is also like a bound on the generators of the degrees of the generator?
No, I don't think so.
No,
it's not.
So
I think here Grosvenor basis could kick in, could be worse. So that was only talking about one annihilator.
yeah.
So when the annihilating ideal is principal, then it is fine, of course. But when it is non-principal, it could be very bad. Yeah, but I have to think about that. Maybe these results imply something there. So in general, you cannot, just by Grosvenor basis, you cannot deduce anything. Okay. Second, sorry. Yes. Oh, 2 minutes. I thought you said 5:20. 5:15. Okay. Well, you have seen one version, so I guess others I can. So annihilator at 0 is the question whether every annihilator of this polynomial map vanishes at 0, or the constant term of every annihilator is 0. And that question is actually equivalent to ZC. This can be seen easily. Let me skip it. So this annihilator at 0 question is also in X space. It's an equivalent question. And third, the most interesting interpretation of this is, or equivalent formulation of this question is the following, which we call approximate polynomial satisfiability. So this is a generalization of polynomial satisfiability. So here you are not looking for a root, but you are looking for these rational functions in a single variable epsilon, such that when you evaluate fi at these points betas, at this point beta, you don't care about 0, you just care about it being a polynomial that is a multiple of epsilon. Okay? So you should think of this as mod epsilon. So you want rational functions beta such that fi at beta is 0 mod epsilon. Okay, so it's a completely algebraic question, but the analysis is of course, the motivation is of course from real analysis. So you should think of epsilon as tending to 0, and in that case it is like when you evaluate fi at beta, it becomes arbitrarily small. Okay. While beta may become arbitrarily large, because beta may have 1 over epsilon. So basically the betas may extend to infinity, but fi at beta may tend to 0. So this problem should actually be called infinitesimally approximate polynomial satisfiability, because it is not just an approximate root, but it's a infinite sequence of points where the system evaluation is tending to 0. okay, arbitrarily close to 0. This question is also equivalent to ZC, and this is not trivial. Something called the Lemke-Lichtich result is needed for this. I'll also skip this. This is way too complicated. So this question is in X space, and this APS is the question which we have put in P space. But there is no time for that now. So let me just jump to so this in particular covers GCT Chasm, because this VP bar hitting set generator verification problem can be reduced to APS. And in fact, anything to do with approximation can be, or approximative complexity can be reduced to it. So all those things are special cases. Let me skip the proof. So I can discuss the idea offline. So in the end, what we did is algebraic dependence testing we showed in intersection co-AM. What is open is finding any sub-exponential time algorithm for this. For say p equal to 2. So everything is open there. Approximate polynomial satisfiability we show in P space, and we want to bring it down. And Ketan's challenge is to bring it in PH. Right? So this will give you an alternative to GCT.
Yes. Serious possibility.
I'm not sure whether it is serious. Okay. So one natural instance which is open for both the problems is look at set of quadratic polynomials mod 2. Okay, so we don't know AD, neither do we know APS for this. Okay, thanks.
So, you didn't show us the proof, I just one word about it. Does it involve a degree bound for these approximate annihilators or whatever? Is the analog of annihilators when you want the constant term to be?
It will use the beginning of modern algebraic geometry. So in particular, it will require Bezout degree bound. But it will not require Perron bound. So it will be the same bound, but in a different setting, in a different place.
So a related question to the degree bounds is we often know that, you started with a given polynomial map, but in the context of heating sets or many other contexts, we can choose, more polynomials where the transcendence degree is way smaller than the number. And then the degree bounds become down from exponential to polynomial.
Yes.
This helps you in any way?
No, so we were interested in this problem, and here f is given to us in the input.
I understand, but in these cases where
in the cases, in the heating set generator question, the verification question.
Yeah.
So in the verification question, somebody gives you an arbitrary candidate set. So there again, it's not in control.
It won't help you because even if you have a polynomial degree bound, there's still
it's exponential system, I know, but I'm just wondering for the approximate thing whether it's.
No, because even in the approximate thing, he's still using a degree bound to solve some linear system equations, just for the constant term being non-zero. So it's basically the same algorithm as transcendence degree, the p-space algorithm, but with an additional constraint. So even if the degree bound is polynomial,
it doesn't help.
Doesn't help.
Yeah, because in this question you have to go over all the annihilators and ensure that the constant term is 0. So for such annihilators where the constant term is 1 or non-zero, Perron bound may not be applicable. You don't know where those annihilators, bad annihilators lie.
So I guess what you're saying is that the number of coefficients is exponential anyway.
Right.
Yeah, okay.
Any other very quick questions? Okay, let's take all the other questions offline.
Thank you.